Okay, so this week I'm going to show you guys how to find the electric field outside of a sphere of charge using Gauss's law. Now I wrote Gauss's law right down here. It's the surface integral of the electric field dotted with the surface, and we set that equal to the charge enclosed, Qn, over epsilon naught. Now when doing these problems, we have to split up. We usually split the left hand side and the right hand side. Before we even do that, first thing we need to do is figure out what kind of a Gaussian surface we're going to use. So for a sphere like this, a good Gaussian surface is going to be a sphere. We do this because when we look at this surface integral right here, we have a dot product. First thing in our dot product is the electric field, which is coming from the sphere of charge. It's going to be going out like this. We dot it with the ds, which is the Gaussian surface. We're going to dot these two things, and this is the vector of the normal. This is the normal vector of the surface. We do this because the angle in between these things is going to be 0. And so when we set up our dot product and we carry it out, I'll show you. It just kind of goes to 1, and then we have a multiplication left here. So first let's do the E dot ds. It's going to be E dot ds. These are vectors. And that's going to be equal to the magnitude of the E times the ds times the cosine of theta. And as we see, when this is the theta right here, it's going to be 0. So when you have a cosine of 0, it just goes to 1. So now instead of taking a surface integral of two vectors, we can take the integral of two scalars, which is a lot easier because the electric field is constant. So we can bring that out front. And then we're left with ds. That's going to equal just E times S. Now what the S is the surface area of the sphere. So we set S equal to 4 pi r squared. And now we're done with the left side of our equation. We just solved this double integral, or this surface integral right here, taking advantage of this Gaussian surface. So we have a E 4 pi r squared equals Q enclosed over epsilon naught. Now for the example that I'm showing you right now, example 28.3, the charge distribution inside the sphere is constant. So we don't have to really do the double integral, or I mean the triple integral for the volume, and have to do all that calculus. We can pretty much say that the charged enclosed is just going to be the charge from the sphere. So this thing that we calculated earlier is just going to equal Q over epsilon naught. Last thing we do is we solve for E. Q 4 pi epsilon naught r squared. Now what does this look like here? It looks like our K constant. Oops, sorry. So that's our K constant. So now we just have E equals KQ over R squared. And that is the electric field outside of our sphere at any point R. Just got to plug in what our R is, and we're going to find the electric field.